Swayam Prabha. Digital India. Educated India.
So in this lecture, I'll be talking about modeling of open systems from a stochastic point of view. I'm talking about reaction kinetics. You looked at several reaction kinetics in the previous classes, where we had a homogeneously mixed system mimicking a batch kind of a reactor. But there are, in chemical engineering, many processes are actually semi-continuous or continuous, where mass come in and then mass leave, and then you have a reactor. So I want to kind of talk about two problems today. One is a semi-batch reactor where some reaction is happening, and then a continuous stir tank reactor, CSTR, in which a reaction may happen. First, I will present the details in terms of a deterministic approach, and then we see how we analyze such problems, and then we take a stochastic approach and discuss the same. Okay, so two problems. Semi-batch and CSTR. So we imagine in both cases something like a first order irreversible reaction A going to B occurs. Okay. So the deterministic approach of modeling these systems are already there in many literature and books. So it's just going to be more like a recap. All of you have done CRE course before? CRE course? Okay. So then, so what we mean by semi-batch here is that you have a reactor, okay, and then you basically feed a stream containing reactant A. Okay. So basically this gets filled up as a function of time, and then the reaction A to B is also happen here. Okay. So our question here would be, as a function of time, what is the concentration of A in here, or what's the conversion of A here, and so on. Okay. So what we do in such problem is that we write a mass balance. Okay. We write what is coming in, what is leaving out, how much is generated, and that should be equal to accumulation. Okay. So we say something like in minus out plus generated must be equal to accumulation. Okay. We write what is called mass balance or a mole balance. So in this case, what is coming in is some molecule is coming in here. So we say that Ca naught into V naught. So Ca naught is the concentration of reactant A in this stream, and V naught here is the volumetric flow rate of the fluid coming in. Okay. So Ca naught times V naught will tell you how many moles of A is entering the system per unit time. That's what's coming in. So this is a semi-batch, so nothing is going out. So obviously this out term is actually 0. Then we have this generation term. Okay, so we say this is RA V. This is this is basically a reaction rate, number of moles of A reacted per unit volume per unit time, times the volume of the reacting mixture. This V is not the total volume, it is the volume of the reacting mixture at any point of time t. So in this case, V itself is a dynamical quantity, it's going to change as more and more fluid comes in. And then we have an accumulation term, which is nothing but d by dt of Vc. Again, this V is the volume of the reacting mixture, C is the concentration at any point of time t. Okay. So you would write a similar this kind of a mass balance equation. Okay. Now it's all about how we write the V and RA and so on. So here minus RA is given as some KCA. Okay. So this is first order irreversible rate kinetics, and then we also want V. If the volumetric flow rate, the incoming volumetric flow rate is steady constant, then we can write V is equal to some initial volume plus V naught times T. Okay. So the volume of the reacting mixture is going to increase linearly with respect to time. Okay, so this may be 0 or some finite value. So you can see that there are two in this equation. There are two things. One is the volume, another one is concentration. Both are functions of time. We primarily are interested in the time change of concentration, and now we can substitute for volume using this independent mass balance on the volume of the reactor. So we can substitute all that. So this quantity is constant. So I am using this capital V naught for the initial volume of the mixture and small v naught here as the volumetric flow rate of the incoming stream. So you got this. So this you can write as Ca dV by dt plus V, okay. This dV by dt here is nothing but V naught. So here I have Ca naught minus Ca times V naught So between here I have brought this term to the left and then divided this entire terms with this quantity. Okay. So then what you will have here is Ca naught minus Ca times V naught divided by V naught plus T plus Ra, because this is divided out, and then on the right hand side you will have only dCA by dt. Okay. Suppose if you take initial volume is 0, this becomes a little simpler. Now we can substitute for Ra. So you will get a kind of a first order rate reaction equation that tells you that how concentration of A will vary with respect to time. Okay. Just check if I missed anything here, because I should be expecting a V naught term there. It's all good. Okay, so you probably need a initial condition, and then you will solve this, get C as a function of time t, and then get conversion and so on. So, okay, so this is what we do in terms of semi-batch deterministic approach. Okay, so now we want to look at the same problem from a stochastic point of view. So when we deal with this stochastic approach, we know how to handle this A going to B in the bulk. All we need to worry about is how do we model the injection of molecules of A into the system. Okay, so that's what the new term here. Otherwise, it's otherwise we already looked at how to solve a batch reaction for this case. So in the stochastic approach, we have this A going to B with some rate constant K. Okay, this we have, and then to model this incoming injection, we can imagine this is another reaction where you have some source bringing in some A. Okay, so I'm just mapping this open system into a cascade of reaction system that mimics this inputting of this injection of this molecule A. This happens anyway. Now A is also getting created as if somebody is putting some amount of A with some constant here. Okay, and this constant we can say something like maybe A or something like that. And of course this A is going to depend on the volumetric flow rate, initial concentration and all that. So then we have to basically handle these set of equations, and the master equation, chemical master equation that represents this scheme will actually model the semi-batch reaction system. So we write that dPn. So we are asking what's the probability of finding n number of A molecule at time t in a reactor. So first for this reaction we write K times n plus 1 P of n plus 1 minus Kn P of n and then we also have only two terms will be there. So when the state is at n, a reaction will lead to n minus 1, so that is a death term. When the reaction is at n plus 1, a reaction forward reaction can become n plus 1 to n, so this will create the probability and this is a loss. So here we don't have a reversible reaction, so it's only irreversible reaction. Suppose if you have a reversible reaction, then we have additional terms. We have seen many examples before already. Okay, but now we have to worry about this term also. Okay, so here what will happen is you have, when the system is at n at some constant, this will get created and it will be also destroyed by this. See, here is a constant rate of addition. Okay, when the system is at n minus 1, A times P of n minus 1 will be the rate of generation of probability, because it adds one molecule. Again, we are talking about a step, a jump process where one molecule at a time reacts or enters as independent events, so that we justify it's a Markov process, and these are all independent events. So this term will tell you that if the current system is at n minus 1, an injection step will take from n minus 1 to n. On the other hand, if the current system is at n, one injection step will take it to n plus 1, so you have a lost. Okay, so this chemical master equation basically represents this kind of a semi-batch reactor. So now all you have to do is you have to define your rate constant depending upon the temperature, and then this A here to represent what is the rate of injection, rate of addition. So that in other words, this A basically means approximately CA0 times V0, number of molecules. So this is written in moles, but you have to convert this into number of molecules, and this will tell you number of molecules per unit time that you are adding. Okay, so that is rate constant A. N equal to 0, what will happen? What will change? Yeah. Yeah, so suppose even if you start with the 0 molecules of A, this reaction will put more and more A, okay, and then this will take over from there. So then the relative weights of A and K will determine what is N. Okay, so when you solve this, what you get is you will get P of n comma t. What is the probability of finding n molecule at time t? N can be 0, 1, 2, 3, 4, etc., etc. So you are basically going to get a probability distribution of finding n molecule in a system. Why that information is important? If I have this, I can always find n of t by this. I'll get the mean value of n as a function of time t. Okay, and then if you want, you can also get the standard deviation, variance, etc., etc., because I know P of n comma t. This is something you can write a small Python code to numerically solve this. Get P of n comma t as a function of time, get the mean and standard deviation and plot it, and then you can see, and compare also with the deterministic approach. Okay, so now let's look at the continuous reactor. In the continuous reactor, what happens is we think about a steady state operation. Okay, so V naught, CA naught is the incoming stream, V naught, CA is a leaving stream, and this is perfectly mixed, and the volume of this reaction mixture is constant at steady state. Okay, so I'm looking at one example where there's an unsteady state behavior. Now I'm talking about a steady state behavior. CSTR we mostly handle in a steady state behavior. So clearly there is no accumulation term here, right? Steady state, nothing changes with respect to time. So what is coming in? CA naught into V naught. This is what coming in. What is leaving? Volumetric flow rate. I'm talking about constant density, so V naught is not changing and all that. Liquid phase constant density reactions. So we've got V naught into CA plus RAV, where V here is the volume of the reaction mixture. In this case, volume of the reaction mixture, volume of the reactor, they are all the same. It's not going to change. So what you get from here is we get V naught into CA naught minus CA equal minus RAV, and CA naught minus CA is equal to minus RA, and then you have tau, where tau is the volume of the reactor by the volumetric flow rate. So this is the design equation for CSTR. Okay, now you can substitute for minus RA as KCA. Okay, so minus RA is equal to KCA. Substituting it here, you would solve something like the concentration in the reactor is Ca naught by 1 plus K tau. K is the rate constant, tau is the space time of the reactor. So you can see that by designing a reactor with a larger volume, smaller volume, you can change this tau, or you can change for a fixed volume, you can change the volumetric flow rate and change tau. Ca naught is also under your control. K you can change by temperature. So you have some option to manipulate each of these variable. Accordingly, the steady state concentration in the reactor will change. Okay, so this is how we handle CSTR at steady state. So when you try to think about this steady state CSTR from a stochastic point of view, here there is no time dependence here, right? This is just a constant value. But in stochastic approach, we can get not only the mean behavior but also the fluctuations. The mean concentration or the mean number of molecules will become time independent, but it will have an associated fluctuation and variations. Okay, so that's what we can infer from the stochastic approach. Okay, so in the stochastic approach, again we already know how to handle this inlet behavior, the injection, which we already saw for semi batch. Now in this case, all we need to do is to model the outlet. In the outlet, you have to think about what reaction can represent this exit process, how molecules of A is lost by this effluent. Okay, if you add that, then we know how to solve this problem. So for injection or input, we think of some source term adding A with some rate constant A, this already we saw, and then reaction A going to B with some rate constant K. Now when you think about this output or outgo, so you have to say this is something like A going into some theta, which is more like a dead state, it's gone, not going to come back. Okay, so here we say some rate constant B. Note that the rate of addition and rate of removal, they are not the same, they need not be the same. Why? Because here this is added at a constant rate depending upon the initial concentration and the volumetric flow rate. This one on the other hand depends on what is the current amount of A in the reactor. Okay, so it has to be dealt like a first order reaction. The rate of removal depends on the current concentration in the reactor. Look at this. Okay, it depends on what is there in the reactor Ca. So we have to sort of think about this. In other words, if you think about these two, they are basically the same kind of reaction with the two different parallel reaction. One giving rise to product B, another one that is taking it away. Okay, so in fact you can define an effective constant K as K plus B, right, and then just deal with only these two. That is also possible. Okay, but in any case we will just take all the things explicitly. So d of dp n comma t, so like before we have A of p n minus 1 minus AP of N. This models the injection or the input. Then we have the reaction. Reaction. These two terms takes care of the removal part or the outgo, that when the system is at n plus 1, when one molecule leaves, and that probability is proportional to B times n plus 1, and when the system is at n, it will lose into n minus 1, so this is a loss probability. So if you look at these two terms, you see they are exactly the same. So in fact, you can think of an effective constant by combining these two. You can say K plus B as some effective constant. So you can just deal with only these two terms. Okay. So now you got an equation for a CSTR. Yeah. Yeah. Because as I said here, in the mechanics of the CSTR operation, what is there in the reactor is what's coming out, right? So in a perfectly well mixed reactor, this will have a particular concentration. The moment it enters, it mixes with the entire container and then reaches another concentration. There's a step change in the concentration from CA0 to CA. What is present in this reactor is what coming out, isn't it? So the probability of a molecule leaving this depends on how many molecules are A present here. But this operation is different. This is regardless of what is there. Even if you have no A or extra A, this will keep adding. Okay, like a zero order rate. But here on the other hand, whether you will find some molecule here or not depends on how much you actually have here. This stream is not an independent stream like this. So therefore, we model the outlet stream as a first order rate that is proportional to the number of molecules. In fact, I can give you some what you can do. Suppose let's say this is not a first order rate. I can put a bimolecular rate, right? So then these two terms will become different now. Okay, this will become n plus 1 square and this will become n square, but this term will remain still proportional to n, because outlet stream is always a first order like process, because it just depends on the number of molecules at that time. But reactions can be first order, then you can combine these two. If it's anything other than first order, then you have to deal this separately. Or if this is itself is a zero order reaction, then this can be combined with the injection part. So you can see how many combinations you can think about depending upon the rate kinetics. Okay, as far as this system is concerned, the inlet stream is a zero order process, outlet stream is a first order process, reaction can be anything. Okay. So by the way, the treatment of semi-batch and CSTR stochastically is not there anywhere. There is no literature on that. So what we are just discussing today is a new knowledge. Okay. So if you build on it, we can write a paper about it. So this is a nice project if you can work on. Maybe one of you can take semi-batch operation, set up the equations, solve some test cases, compare the results with the deterministic approach. Similarly, another group can look at the CSTR, set up the stochastic and deterministic equations, solve them and show the comparison between the two. And one can write a paper about that, because it's not there in the literature. It's not been done before. So and again, like I said, we took this very simplified rate kinetics, but you can have any other combination, multiple reactions, parallel reactions, series reactions, whatever you want, you can have it here. But again, we are talking about a single variable problem. If it is become necessary that you have to track multiple combinations of molecules, you'll have to look at some n-dimensional problem here, two-dimensional, two variables representing the system, 3 variables representing the system, so on. So you can see that you can really make it as much complicated as possible depending upon what you have got. Okay, for example, if you want to solve this in a Michaelis-Menten reaction, then you may want to track enzyme substrate as a function of time. You'll have a 2 variable. Okay, but as long as you know how to handle the injection and removal, then this something can be set up. Okay, so think about it. This is a nice topic for a project in this course. Okay, so that's all I got to say about this chemical master equation or a step process or jump process. What I will be doing is tomorrow we have a 5 o'clock class, right? Usually, okay. So that class is cancelled. I'm not here, and the next whole week I'm sort of traveling. And next week is also quiz on Thursday. Thursday I may be here for the thing, but no classes next week. Okay, so take this time to prepare for your exam. And then the week after, when the classes commence again, I'll be talking about a subset of this Markov process called Markov chains. Okay, so Markov chains are very useful from a chemical engineering point of view. You can deal grinding, many mechanical operations, transport processes, and etc. So we'll take some examples of that problem. Conceptually, it's far more simpler than this, and it's more useful for a chemical engineering processes. Okay, we'll deal something like that, and then after we discuss Markov chain, then we'll go to the continuous Markov process, and then towards the end of the course, we will do the kinetic Monte Carlo simulation to solve all these problems in a numerical setting or a simulation setting. So that's how the roadmap is going to be. And as far as the quiz 2 is concerned, I think read all the notes from quiz 1 onwards, okay, until today. So that's the portion. All the class notes have been updated and uploaded in Moodle. Use that material. Don't look anywhere else, because it's very easy to get confused, because this is a process, this is a field where a lot of mathematicians and physicists are working pretty much, and then instead of looking at application, they look at a lot of mathematical development and proof. So don't get lost. Okay, try to be just, take a look at the notes, your class notes, and the notes are uploaded, and then go through the references I have recommended in those notes. Okay, those are very specific references that will give you a little bit more aid for your reading and comprehension. And don't try to read something from ChatGPT or any other online material, because it can lead to a lot of confusion. Okay, I have fallen to the trap when I was a student, so don't do that. Okay, just stick to this, and then maybe once you finish the course, you think it's very fascinating or interesting, then do research or do more projects, whatever you like. Okay, but as far as this course is concerned, just be specific about this. Okay, whatever you need, it's there in the notes, and just build on it from there.